Welcome! In this lecture we will see how to analytically solve a specific type of ODE, in particular the linear ODEs. Here we have the definition of a linear ODE of order n, and any differential equation that can be rewritten in this manner, it's said to be a linear ODE. Now, what is important is that the derivatives of the function appear here, just multiply by some coefficients that only depend on t. So, basically what we are saying here is that the derivatives of the function appear like a linear combination where the coefficients only depend on the variable t, also called independent variable. Whenever we can rewrite an ODE in this manner, we say it is linear. Now, let's see if we understand this definition. Here we have some examples of linear ODEs. For example, this is a linear ODE. You can see here we have x to the power 3. And I'm saying this is a linear ODE. This makes sense? Well, yes, because the definition of linear ODE applies to the derivatives of the function and how they appear in the ODE. Here, the derivative of the function appears in a linear manner. In this case, what we have is that the coefficient that multiplies y prime is just 1. So it's a coefficient that does not depend on y. That's the important thing. Whatever we have here in the right-hand side, which does not depend on y, this can be a nonlinear function. Let me go back to the definition. You see here this f of t can be any function of t. It could be t to the power 3, it could be the cosinus of t, it could be any nonlinear function, because the definition of linear here applies to this part, on how the derivatives appear in a linear manner. Another example, this equation here is linear because in this case, the unknown function is u and it depends on t. And we can see that u and the second partial derivative of u both have coefficients that only depend on t, so they appear in a linear manner. However, here we have some example of non-linear ODEs. For example, here the unknown function is y and it depends on t. And as you can see, the first partial derivative here is with a power 2 there. So it doesn't appear in a linear manner. It cannot be rewritten as we have seen here. You can see here that the derivatives never can have a power on them, okay? So another example of a nonlinear ODE would be this one we have here. That's because in this case, the unknown function is u, in this case as a function of x. And in this case, you see here that the unknown u appears inside the cosinus function. So of course this is not linear. This can be never rewritten as appears here, okay? Also, this term here, it multiplies u by the first derivative of u. Again, this is a non-linear term. Okay, now today we will explain how to analytically solve a specific type of linear ODE, which is the first order linear ODE. So today we will concentrate in this type of ODE. Okay, this is okay, I'm trying to do the square here. Okay, so here we have a constant, a coefficient that multiplies y prime plus another coefficient that multiplies y equals a right-hand side that only depends on the independent variable t, okay? So in general, any first order linear ODE can be written in this manner, because if it's a first order linear ODE, we will always be able to rearrange it in this way. Now we will see today that this type of ODE can always be solved analytically. Now, this is just a remark, okay? In case that when we want to solve this type of ODE, it happens that A0 is 0, so it happens that this term is not there, then we have this equation you can see here, yeah? The first partial derivative, I can take this term and divide here, and I get this equation here, okay? Now, of course, this is a separable ODE. In fact, we see that we can just integrate, yeah, to obtain the solution of the differential equation. So this is a very easy case where we can solve this type of ODE. But in general, of course, this term is not going to be 0, so we need to know how to solve it in that case. Okay, so here we need a definition, and the definition is what is an homogeneous differential equation. Well, for linear ODEs, we say that they are homogeneous when f of t in the right-hand side is 0. So in the previous definition, the f of t we had here is equal to 0. In that case, we say that the ODE is homogeneous. So, in particular, an homogeneous first order linear ODE can always be rewritten in this manner. Yeah? Okay, so we will say that when given a first order linear ODE, like this one that we want to solve, we will say that it has an associated homogeneous ODE, which is the same ODE, but where we change f of t to 0, okay? This is very important. We will use a lot the associated homogeneous ODE in order to solve this initial ODE we wanted to solve. Now, here is a very important theorem for today's lecture. Given the first order linear ODE that we want to solve, that looks like this, and given a particular solution of the ODE that we will call yp, and the general solution of the associated homogeneous ODE that we will call yh, this h because it comes from homogeneous, okay, and the p here is because it comes from particular solution, then the general solution of the initial ODE is just the sum of the particular solution of the homogeneous plus, the particular solution of the ODE plus the general solution of the homogeneous. Let's see if this is true. Let's prove the theorem, okay? Now, the proof is very simple. We have the general solution of the associated ODE, which is yh. This is the general solution of the homogeneous ODE. And we know that yp, let's choose another color, and we know that yp is a particular solution of the initial ODE, okay? And we wrote here the equation that is satisfied by yp and the equation that is satisfied by yh, okay? Yp satisfies the initial ODE, which is equal to f of t. Yh satisfies the homogeneous ODE. Of course, a1 and a0 here are the same coefficients. Then, if I substitute in this equation, I substitute in here y by the sum of yp plus yh, I will obtain the following thing. Now, if y is the sum of yp and yh, obviously y prime is y prime p plus y prime h. Now, when I plug in this equation, a1 is a1, y prime t is this thing, so I will put this here, yeah? And a0 plus a0, and then yt is the sum, which will go here. And then I will make these calculations, a1 times y prime plus a0 times yp. I'm writing here together the terms that involve yp, and then writing here together the terms that involve yh. And what it happens is that, in fact, what I'm writing here is this equation. You can see here that this is exactly, let's use the other color, sorry. Let's use green for the homogeneous, and okay, so you can see that this is exactly this equation, and you can see that this is exactly this equation. So, of course, this is equal to f of t, and this is equal to 0. So f of t plus 0 is f of t, and we proved that the OD, the initial OD, is equal to f of t when using as yt, the sum of yp plus yh. So this completes the proof. Now, what this means is that in order to solve an ODE, a first order ODE, it's as simple as finding the general solution of the associated homogeneous ODE. So first thing, find YH, then find a particular solution YP, that's the second step to find YP, and finally we will get the general solution that we were trying to find, but by just summing up YP plus YH. What we will see now is that step 1 is very simple, because it will happen that to find the general solution of the homogeneous, it will always be a separable ODE, and we already know how to solve them. That was done in the previous lecture. In order to find the particular solution YP, we will use a new method called variation of constants, okay? And step 3 is very easy after we completed step 1 and step 2. Okay, so let's do these 3 steps using the general equation. So let's start with the general equation. Let me write it here. We are trying to solve a1t that multiplies y prime t plus another coefficient, a0, that only depends on t, times yt equals some function f of t. But in order to solve this first order linear ODE, the first step is to find the general solution of the associated homogeneous ODE. So that means my first goal is to solve this ODE and find its general solution. So I'm changing here f of t to 0 initially. This is the so-called associated homogeneous differential equation. And we can see here that it will always happen that I can rearrange this in this way. You can see here, yeah? This is always possible. Thus, this is a separable ODE because we can rewrite it in a function that only depends on y, that multiplies y prime, and is equal to a function that only depends on t, Remember that this is always a separable ODE if we can rewrite it in this manner. So I will solve it using what we saw in the previous lecture. I will compute the integral. I will compute the integral of the left-hand side with respect to y and the integral of the right-hand side with respect to t, plus an integration constant that can be any real number. Okay? So that's the way we will proceed to solve it. You have this already written here, okay? We solved this integral and it's a natural logarithm. We will solve this integral. Now I will just keep it like this because I don't have a specific definition for this function. But of course, when we solve a specific ODE, we need to solve this integral. And once we compute this integral here, now we will apply the exponentials to get rid of the natural logarithm. Yeah, the exponential of this should be equal to the exponential of this term. And we find out that the exponential and natural logarithm are inverse functions. So what we would find is that this absolute value of y is equal to, let me write it better, the exponential of minus the integral of p plus c, which can be rewritten as this term times another constant that will be always positive because the exponential is always a positive function. Now, in order to get the explicit solution, I will study the different cases and I will find out that y is equal to plus minus this value. That's what we have already done here. So we are here, plus minus this value times this c that is positive. So at the end, what we can say is that the homogeneous solution is equal to a constant that can be in the real numbers because of this plus and minus we have here, and the exponential. Okay? So, in summary, when we solve this step 1, we find out that the homogeneous solution will always look like this. Okay? But the way to find it is just solve it as a separable ODE. Let's go now to the second step. The second step, step 2, is to find a particular solution of the initial ODE we are interested on, which is this one, yeah? Which is equal to f of t, which this f of t could be anything. It's not 0. It could be, but in general it's not. Now we will use a method that is called the variation of constant. The main idea behind this method is very simple. It tries to find a particular solution that is similar to the homogeneous solution. Now, what do I mean with similar? Well, you know that the homogeneous solution is this one. Yeah, it looks like this. In order to write it in a simpler manner, let me say that this is c times something called mu, just to make it simpler. Yeah? You agree that this homogeneous is c times this thing that could be called mu, for example. Okay, so this is what I'm writing here as mu, okay? Now the idea is to try to find a particular solution that looks pretty similar to c times mu, but now this is not anymore a constant value, but something that can depend on t. That's why the method is called variation of constants. What was constant in the homogeneous solution, now in order to find a particular solution, I'm allowing it to variate to depend on t. Okay? So this is the idea. What we need to find is this function kt. How we will find it? Substituting into the ODE. Now this function kt will be found by imposing that this yp, that is written in this manner, satisfies the initial ODE. So the main idea is to substitute it into the ODE and impose that it satisfies the ODE. Now let's do it. Here we are trying to find a particular solution that reads like this. Remember that my initial ODE is this one, a1 y prime plus a0 y equals f of t. And I'm trying to find a function yp that looks like this. And I want to know who is this function kt. Okay, that's the unknown, let's say. Okay, so I want to substitute yp inside the ODE. So what I will do is I will plug in here yp. Okay, now I have yp. I need to compute y prime t, which is computed here. Very simple. This is a product. So k prime times mu plus k times mu prime. Okay, and now I will substitute y and y prime, y and y prime into the initial ODE, which is this one here. Okay, the initial ODE, which is this one here. If we do that, okay, here we have the initial ODE. I will copy a1, and where I find y prime t, I will plug in here this expression, y prime p. Then plus a0, and where I find yt, I will plug in here yp. Now, I can see here that I can put together the terms that multiply k and the terms that multiply k prime. And if I did if I did the steps properly, it will happen that everything that multiplies k vanishes. It's equal to 0, okay? That will happen because mu is an homogeneous solution. So this is the homogeneous equation. So that will, that's the reason this term vanishes, okay? And what remains here is that, okay, this equation should be equal to f of t because it's the non-homogeneous case. And from here, I get this equation in green color we have here. And of course, from this equation, I can isolate k. We can from this equation isolate k prime t. And it would be f of t divided by mu a1. Now this is k prime t, but I'm interested in finding k. So of course, in order to find k, I will need to integrate this. So kt is the integral of this term that we found. And once we solve this integral, we get the value of k and we get the particular solution, which is this value of k we obtained times mu that was already computed. So finally, a summary on how to solve first-order linear ODEs is first, compute the general solution of the homogeneous equation. It will always look like this. Then find a particular solution of the non-homogeneous equation, the initial equation, using the variation of constant method, and you will find the value of k that you need to use here instead of the constant value c that you are using in the homogeneous. And finally, you will sum up yh plus yp in order to get the general solution of the initial ODE that we were trying to solve, which was this one. So at the end, you will find the general solution that will depend on c, one constant, as it is a first order ODE. Now, let's see if we understood all the steps trying to solve a particular ODE. Now let's do an example. First order linear ODE. Now, let's see. We will solve, for example, this equation, 1 over t squared y prime t plus 3 times yt equals 1. First thing we need to do is to check if this is first order ODE. Is it first order? Yes, it is first order because the highest derivative that appears here is y prime. Okay, is it linear? Yes, it is linear because the coefficients that multiply y prime, the coefficient that multiplies y prime, that could be called a1, only depends on t, and the coefficient called a0 in the slides that multiplies y, it only depends on, in this case it's constant, but what is important is that it does not depend on y, yeah? And the right hand side is a function that only depends on t. In this case, again, it is constant, but what is important is that it does not depend on y. So yes, we checked that it is a first order and linear ODE. So we can use in order to solve it, we can use what we saw in this lecture. So let's proceed with step 1. Step 1, remember, it is to solve the associated homogeneous equation. So we want to solve h plus 3 times yh equals 0. Okay? So that's the first thing we want to solve. We want to find the general solution of the homogeneous equation. How can we do that? Well, we know that this should be a separable ODE. We did that in general, so in this particular case, it should be possible also. For example, I can write this second term in the left-hand side. And then it is very simple to see that I can rewrite this as 1 over yht that multiplies y prime h equals minus 3t squared. Okay, I divide it by yh and multiply it by t squared and obtain this. Okay, of course, this step we are assuming that this is different from 0. Okay? Okay, now, this is a separable ODE. I can solve it just integrating 1 over yh with respect to y. And the right-hand side, I will compute the integral with respect to t plus a constant, integration constant, that can be any real number. Okay, now I will solve this integral. This is the natural logarithm of the absolute volume of yh, which is equal to, oh, that there's 2 minus, sorry, one minus only there, okay? So this is minus, now the integral of 3 times t squared would be t to the power 3, yeah, but when I compute the derivative of this, is it's already 3 times the square, that's it, yeah? I don't need to do anything else. And then I would do plus c for any constant. Now, if I want to find the explicit solution, I will use exponentials. So the exponential of the natural logarithm of yh is going to be equal to the exponential of minus t to the power 3 plus c, which can be rewritten in this manner. Yeah, where now this c hat must be positive. Yeah, because in fact this comes from e to the power c. The exponential is always positive, so that's the reason c hat is always positive. Now, the exponential and natural logarithm are inverse functions, so what I get here is that this is the absolute value of yh. Now, if I study cases of the different signs, I will find out at the end yh is equal to plus minus c hat times the exponential of minus t to the power 3. And at the end, we normally reduce this to, okay, if this plus minus something that is always positive, okay, let's say that this is another c value that is any real number you want, but not 0. That's it. Okay? So we found the solution of the exponential, the solution of the homogeneous equation. We will reserve this. And this is the end of step 1. Okay? Step 1, we solved the separable equation and we got this. Let's move to step 2. Step 2 is to find a particular solution of the initial ODE, which is this one. Okay? So in order to do that, step 2, find a particular solution of the initial equation. Let me say that this is equation 1. Okay. In order to find this, we will use the variation of constants method. Its main idea is to try to find a particular solution that looks pretty similar to the homogeneous, but instead of the constant term we have here, we will have a function that will depend on t. Is a product, okay? So I propose to find a particular solution that is similar to the homogeneous general solution, and I will try to find what should be this function kt in order to have a particular solution of the initial ODE. How do I find this value? Well, we will substitute yp into the initial ODE. So I will need y prime p. Y prime p is k prime times the exponential plus k prime t. No, sorry. Plus kt times the derivative of the exponential is itself, but then I need to compute the derivative of the exponent, and that is minus 3t squared. Okay? Now, we will substitute yp and y prime p in the initial ODE. Okay? Let me go back to the initial ODE. Is this one? Okay? Let's use this initial ODE. And let's put it here. Okay. So we will substitute in the ODE 1 yp and y prime p. Let's do it. The ODE is 1 over t squared times y prime p. Y prime p is k prime exponential of minus t minus 3 times t squared k exponential of minus t. Now plus 3 times yt. Yp is k times the exponential. And this should be equal to 1. Now let's put together the terms that depend on kt. Kt appears here. Yeah. We can see here that this t squared is multiplied by this term, so it will disappear. I will get minus 3k exponential. And then I have another term here, which has k. So I will have plus 3 times the exponential. So what we can see here is that these two terms are equal with different sign. So we find out that this is 0. That's what we were expecting, because when we saw in the theory slides, is this case. This will always happen if we did not do any errors before. The term that multiplies kt should vanish because it's the solution of the homogeneous solution. So that really makes sense. We are in the good way. Okay, let's proceed. Plus, so I already used this term, I already used this term. This is the only left. And this term is k prime t, exponential of minus t, multiplied by 1 over t squared, and this should be equal to 1. Yeah. So from here I can isolate k prime t, and k prime t is equal to t squared times the exponential of t to the power 3. And I found I find this value of k prime t, but what I'm really interested is in kt. So who is kt? Is the integral of t squared exponential with respect to t, and the result of this integral, this is a direct integral, it's just the exponential of t squared, t to the power 3. If I compute the derivative of this, I get the exponential times the derivative of the exponent is 3 times the square. There's not a 3 here, so I will divide by 3. That's it. So at the end, I find that yp is k times the exponential. So I found the value of k. So finally I can write here that ypt, the particular solution I was trying to find, is the exponential divided by 3. This is kt, okay, times the exponential of minus t to the power 3, this term here. Okay, so of course these two terms cancel and I get this constant function 1 over 3. So yp is equal to 1 over 3. So step 3, the last one, and very simple, is that the general solution of 1, the initial ODE we wanted to solve, is the sum of the homogeneous, the general homogeneous solution, and the particular solution we found. So let me go here. YH is C hat exponential of minus t to the power 3. So C hat exponential of minus t to the power 3 plus yp, and yp is 1 over 3. So this is the final solution of the differential equation we wanted to solve. Very important, this c is any real value but not 0 because of the exponential, and that's the final solution of the problem. Here in the slides you can find the solution of exactly the same ODE. The only difference is that the independent variable is called x instead of t, but it's the same differential equation, and you can see that they obtain the same solution for the homogeneous general solution and the same solution for the particular case. So at the end, they obtain the same general solution of the ODE we wanted to solve. After solving an ODE, we can always check whether the solution is correct or not. We can check, is it true that this expression we found here, is it true that this expression is solution of the initial ODE? Well, it is as simple as plugging into the differential equation y and computing y prime from this expression. So we have y and we have y prime, and we can substitute into the differential equation and check whether this is correct. So this is what I wanted to explain today. Here in the slides, you have other examples you can try to do yourselves using the slides. This is solved step by step. You have this example and another example here. And also you have a guide here on how to solve this using Maple if you are interested in. And finally, another example, you can try to solve it by yourself and then check the notes. Okay, you have several examples here. So finally, as a remark, in the notes here in the slides, you will see that there are always two terms that have to cancel. It is very important that the terms that multiply k cancel. If that doesn't happen to you, it means you have an error. You have to review your previous steps. Finally, just a comment. We have seen by now separable ODEs and first order linear ODEs. This is not an exclusive, they are not exclusive sets. So you can be just a linear ODE, you can be just a separable ODE, or you can live in both sets. So for example, this ODE here is at the same time separable and linear. So in that case, you can choose what method you prefer to use. In general, if you are asked to find the explicit solution, I recommend to use the method to solve linear ODEs. In case you are told that just finding the implicit solution is enough, maybe it's easier to solve it as a separable ODE. But you can use either of the two methods because, of course, you should find the same solution. And finally, you have here some proposed exercises where you don't have the step-by-step solution, but you have the final solution to check it out. I would recommend to try to solve the last one because it has also an initial condition to find the value of the constant. So this in fact is an initial value problem. You have the ODE, but also you have an extra condition in order to fix the value of the constant in the general solution. So that's it for today's lecture. Thank you very much and see you in the next one.